Hello, welcome to EPG Pathshala Biophysics, Paper 2 Quantum Biophysics. I am Angshuman Lahiri, Associate Professor, Department of Biophysics, Molecular Biology and Bioinformatics, University of Calcutta. In this paper, today we are going to discuss Module 14 dealing with charge distributions and bond orders in molecules. In the Hückel molecular orbital method developed in the previous modules, we have found that for planar conjugated systems, each carbon atom can be thought to contribute a pi-electron that is delocalized over the entire molecule. This can be either along a straight line, for example in butadiene, or in a ring, for example in benzene. If the contributing atoms are carbons, the delocalization is uniform over all the carbon atoms. This can be stated in another way by saying that the charge density on each atom is equal. But for heteronuclear system, this will not in general be true, since the Hückel parameters will be different for, say, nitrogen from those of carbon. In such cases, due to difference in the electronegativity of these atoms, some of them will attract more negative charge than others. Therefore, the charge densities on each atom will be different. In this module, we shall see how one can compute the electron densities from the Hückel molecular orbital theory. We shall also discuss another concept, the bond order, that is a measure of the partial double bond nature of the pi bond. The charge densities and the bond orders are important conceptual tools that help us to understand the structural and chemical properties of the molecule. In this module, our objectives are to learn how we can use the Hückel molecular orbital method to calculate pi-electron densities on the atoms, and also to look at the pi-electronic distribution at the bonds by defining a quantity called the pi bond order. To calculate the charge densities and bond orders for specific cases, taking as examples molecules like ethylene, butadiene, etc. To note how these quantities defined on the basis of the Hückel molecular orbital method can be related to the experimental observables such as bond length and hyperfine splitting. So, it is interesting to note that in our discussion on the application of quantum mechanical principles to chemistry and by extension to biochemistry and biophysics, we are in principle always dealing with nuclei and electrons. The concept of a molecule consisting of atoms as defined in classical chemistry does not automatically arise from these considerations. Lewis's idea of representing bonding between atoms as shared electron pairs provided a bridge between these 2 points of view. It actually provided a guideline for describing molecules in terms of the electron distribution. However, it has proved a non-trivial task for quantitative theory to provide correspondence to such chemical concepts as single, double, or triple bonds. The concept of multiplicity of a chemical bond has proved to be a very important concept in chemistry. Therefore, it was necessary to examine this concept closely from a quantum chemical standpoint, and this gave rise to efforts to quantitatively define bond orders from calculated electron distributions. In our discussion on molecular orbital theory in a previous module, Module 10, we have introduced one such definition. In a diatomic molecule, there are many molecular orbitals, and we cannot say that each pair of electrons populating an MO leads to a chemical bond, although by definition those electrons are delocalized between the two atoms. We distinguished between bonding and antibonding orbitals and introduced the quantity n bond minus n antibond divided by 2 and called it a bond order with n bond and n antibond describing the number of electrons in the bonding and antibonding orbitals respectively. For diatomic molecules, one can note the orbital characteristics and count the number of electrons in bonding and antibonding orbitals. On the other hand, this definition of bond order has not been considered a strictly quantum chemical quantity since it has not been directly calculated from the wave function. Coulson first developed a more rigorous definition through the development of his charge bond order matrix in conjugated pi-electron systems. It is very easy to understand this concept using the Hückel molecular orbital theory. In the Hückel method discussed in the previous two modules, we have seen how the pi-electronic energy levels for conjugated systems could be evaluated. According to the linear combination of atomic orbital prescription that we followed in that method, the molecular orbitals were constructed from n number of 2pz orbitals. And the equation looks like this. The ith molecular orbital given by psi I, that was a sum over the atomic orbitals given by psi j multiplied by the coefficients Cij. The Cij's are the coefficients of the atomic orbital corresponding to the jth atom in the ith molecular orbital. We also saw that the condition that the atomic orbitals are normalized and their overlap with one another being negligibly small leads us to a normalization condition for the molecular orbitals. And this looks like the equation sum over j Cij square equals 1. Each term in the last equation, that is the Cij square, is the electron probability density on the jth atom for a single electron from the ith molecular orbital. So the total electron density on the kth atom will be obtained by summing over all the pi electrons, and that is a quantity which we define as Qk equal to sum over I Ni Cik square. In the last equation, I is the index of the molecular orbital and Ni is the occupation number. This occupation number tells us the number of electrons, whether it is 0, 1 or 2, that are in the molecular orbital I. If Cik happens to be complex, then we replace Cik square with Cik star Cik, where Cik star is the complex conjugate of Cik. Apart from the electron densities on the atoms, we may also be interested in the pi-electron distribution in the bonds. A measure for such a quantity is provided by what is called a pi bond order. And the pi bond order in the Hückel molecular orbital method is calculated only for nearest neighbor atoms I and j. The general formula for pi bond order is written in terms of the product of the coefficients Cij and Cik as Pjk equals sum over I Ni Cij Cik. Here again Ni is the occupation number of the ith molecular orbital. With these formulas, let us examine some specific cases. So we begin with the simple molecule ethylene. In ethylene, there are two pi electrons, both of which should occupy the bonding orbital in the ground state. The bonding orbital we have previously shown to have the form psi plus equals 1 by square root of 2 psi 1 plus psi 2, where psi 1 and psi 2 were the atomic orbitals. So we have C1 equals 1 by square root of 2 and C2 also equals 1 by square root of 2. So for ethylene ground state calculations, we need not bother about the antibonding orbital at all, since its occupation number is 0. So putting the respective quantities in the formula for the electron density, we get Q1 equals twice C1 square, and that is equal to 1, and Q2, that is also equal to 1 because it is equal to 2C2 square. This is a natural result for ethylene since there are no other atoms differing in electronegativity. So what is the bond order for ethylene? There is only one term coming from the bonding orbital. So P12 is given by 2 into C1 into C2, and since C1 and C2 are both equal to 1 by root 2, this comes out as 1. This is also expected since the C-C double bond in ethylene has a pure double bond character and is the shortest. So let us take another example, the case of butadiene. In butadiene, there are 4 pi electrons connected by 3 C-C bonds. Each of these bonds have a partial double bond character. So what are the electron densities on the 4 carbon atoms? Also, what are the 3 bond orders? According to the results of the Hückel molecular orbital calculation on butadiene that we carried out in our previous module, the 4 pi electrons will occupy the 2 bonding orbitals. The coefficients for the bonding orbital 1 are C11 equals 0.37, C12 equals 0.60, C13 equals 0.60, C14 equals 0.37. And similarly, the coefficients for the bonding orbital 2 are C21 equals 0.60, C22 equals 0.37, C23 equals minus 0.37, and C24 equals minus 0.60. The electron densities on the 4 carbon atoms can be calculated by the formula given previously. So Q1 comes out as 2 into 0.37 square plus 2 into 0.60 square, and that is equal to 1. One can carry out similar calculations for the other atoms, and we find that Q2 equals Q3 equals Q4 equals 1. So all of the carbon atoms in butadiene have the pi electron density equal to 1. Again, as a pure hydrocarbon, this result is quite expected for butadiene. The bond orders in butadiene are, however, not identical for all the bonds. For example, if we calculate what is P12, we find that this is equal to 2 into 0.37 into 0.60 plus 2 into 0.60 into 0.37, and that is equal to 0.90. P23
equals 2 into 0.60 into 0.60 plus 2 into 0.37 into minus 0.37, and that is equal to 0.45. And P34, that is equal to 2 into 0.60 into 0.37 plus 2 into minus 0.37 into minus 0.60, and that is again equal to 0.90. Thus, we can see that for butadiene, the two bonds at both ends are similar and have strong double bond character. But the CC bond in the center has a much weaker double bond character, sometimes acknowledged by a broken line parallel to the single bond. This allows rotation around this bond, giving rise to two rotational isomers of butadiene called the trans and cis butadiene. Although in reality trans butadiene is lower in energy than cis butadiene, the Hückel molecular orbital method is too simple and cannot differentiate between the two. The energy difference between the rotational isomers arise from electronic repulsion effects that are different for the isomers, but this is not taken into account in the Hückel molecular orbital method. So let us take the example of a bigger molecule such as benzene. There are 6 pi electrons in a closed ring in benzene, and according to the Hückel molecular orbital calculations that we have carried out in our previous module, all the electrons are accommodated in 3 bonding orbitals. Now, if we put the values of these coefficients in the formulas for charge densities and bond orders, we find that the charge densities for all the 6 atoms in benzene is the same. And the magnitude of the bond orders are also the same and equal to 0.67. This indicates that all the bonds in benzene are equivalent and possess the same partial double bond character. Now let us have a look at a different aromatic compound with a nitrogen replacing a carbon, such as pyridine. Another biologically important compound is pyrimidine, where 2 carbons have been replaced by nitrogens. Taking the case of pyridine, a pyridine is produced when a CH in benzene is replaced with a nitrogen. Now we can apply the Hückel molecular orbital theory to pyridine, since Hückel's rule requires a ring of atoms with unhybridized p orbitals, and nitrogen satisfies that rule. Hückel molecular orbital calculations for pyridine show that for ortho, that is 2 and 5 positions, and para 4 position, the charge densities are positive, while the charge densities are negative for nitrogen and the carbon at the meta position. The bond orders of pyridine look like this. We can see that the NC bond orders are less than the CC bond orders. Briefly discuss about reactivity of molecules and how Hückel theory can help us in thinking about that. The pi-electron populations or pi charges on atoms have been used to explain differences in reactivity pattern. For example, one expects that an electrophilic group is most likely to attack the carbon atom with the largest pi charge. In a similar manner, nucleophilic groups are most likely to attack a carbon atom with the smallest pi charge. Let us take the example of azulene. From Hückel molecular orbital calculations, the pi electronic populations in azulene are as follows. You can see the numbering in the figure. The charges are at site 1, Q1 equals 1.047, Q2 equals Q10 equals 1.173, Q3 is equal to Q9 and that is equal to 1.027, Q4 is equal to Q8 and that is equal to 0.855. Q5 equals Q7 and that is equal to 0.986 and Q6 is 0.870. From these values, we would expect electrophilic attacks to be most likely at sites 2 and 10 and nucleophilic attack on sites 4 and 8. In our previous example with pyridine, we found negative charges at meta position. In this case also, electrophilic attacks mostly occur at the meta position. Nucleophiles attack at C2 or C6 ortho positions where we found maximum positive charge. The Hückel molecular orbital method can be used to calculate the dipole moments of conjugated compounds arising from the pi-electron distribution. The dipole moment of an overall neutral system of point charges is given by the relation mu equals sum over I q by Ri, where mu is the dipole moment, qi are the charges, and Ri are the position vectors of the ith site. The dipole moment vector is not dependent on the choice of the origin of the coordinate system. Therefore, choosing a coordinate system of convenience to calculate Ri, one can easily find the pi component of the dipole moment from the pi charges obtained by the Hückel method. Let us, for example, take the case of imidazole as calculated by Minkin and co-workers. You can see the picture of imidazole and the numbering. The numbering starts from nitrogen, which is number 1, and then 2, 3, 4, 5 along the ring. Using the Hückel molecular orbital method and suitable parameters for the heteroatoms, the charges come out as Q1 equals 0.32, Q2 equals 0.02, Q3 equals minus 0.24, Q4 equals minus 0.04, and Q5 equals minus 0.06. Now, considering the imidazole molecule as a regular pentagon with an internal angle of 108 degrees and the length of each side to be 1.38 angstrom, and putting the origin of the coordinate system on the N1 atom, we can calculate all the vectors from the atoms 2 to 5 and so calculate the pi component of the dipole moment. For the charges taken in this example, the magnitude of the dipole moment comes as about 3.03 dBi. This value is very much dependent on the Hückel parameters chosen. Also, there is no reliable experimental methods to verify the value obtained for the pi component of the dipole moment. One has to obtain the sigma component of the dipole moment as well to compare the theoretical total dipole moment with experimental values. Now let us examine the relation between bond order and bond length. One expects that the strength of the bonds as measured by the bond order and the bond length should have some relationship. If we find a large value of bond order, that would imply a large pi charge in the bonding region and should result in a shorter and stronger bond. The experimentally measured bond lengths and the calculated bond orders actually show this expected behavior. However, the linear relation is not exact if we consider a lot of data involving many types of conjugated systems. The approximate correlation is sometimes good enough for approximate predictions of bond length variations. A relation between theoretical bond lengths and the Hückel molecular orbital bond orders was proposed by Coulson. It has the form given by this equation: R equals S minus d divided by 1 plus k into 1 minus p divided by p. Here S is the single bond length, d the double bond length, P the pi bond order, K is an adjustable parameter, and R the predicted bond length. The single bond length may be taken to be the CC bond in ethane, which has a length of 1.54 angstrom. And the double bond length is taken as 1.337 angstrom. Comparison with experimental data gives the impression that the proposed formula works more or less for condensed ring systems and does not agree so well for acyclic polyenes. Now let us consider a molecule with one or more unpaired electron or electrons. If we place it in an external magnetic field, the interaction energy between the unpaired spin and the magnetic field will depend on whether the spin is up or down. This will give rise to two slightly different energy levels for an unpaired electron. Suppose now that we are radiating this molecule with microwave radiation and trying to excite the electrons from the lower energy level to the higher energy level for these two states. If the energy of radiation is larger than the separation between the energy levels, there will be no absorption. Let us now gradually increase the strength of the magnetic field. Since this will gradually increase the gap between the energy levels, we shall see absorption of the microwave radiation at a certain value of the magnetic field. This would give us a spectrum, that is absorption against externally applied magnetic field with just one peak. Now suppose we are working with a radical which has a hydrogen attached to it. The nucleus of the hydrogen can have spin up or down, and this will have a small effect on the energies of the electron whose spin is making transition between the energy levels created by the magnetic field. The effect will manifest itself as a splitting of the single peak to two peaks. The original single peak is now said to exhibit a hyperfine splitting as a result of the presence of the hydrogen atom. The distance between the two peaks is called the hyperfine splitting constant. This interaction decays rapidly with increasing distance between the electron and the hydrogen. As a result, the hyperfine structure is considered mostly for the cases involving protons directly bonded to a carbon in the pi-electronic system or apart from the carbon by two sigma bonds. In the first case, the proton will be called an alpha proton and the more distant proton is called a beta proton. For an unpaired electron, that is a pi electron, we can hope to apply the Hückel molecular orbital theory for this case. Since the equilibrium position of an alpha proton is in the nodal plane of the planar pi electronic system, the interaction between the unpaired pi electron and the proton is indirect. Such an indirect effect occurs since the unpaired pi electron interacts differently with the alpha and beta spins of the sigma electrons of the carbon atom. As a result, the spatial distributions of these electrons also become different, thereby producing a net spin effect on the hydrogen nucleus. In such situations, the sigma electrons are said to get spin polarized by the pi electrons. The strength of the spin polarization will actually depend on the extent to which the unpaired electron is present on the carbon atom to which that hydrogen is bonded. We therefore expect a relationship to exist between the distribution of the pi spin density in a radical and the hyperfine coupling constants. One of the simplest assumptions is called the McConnell relation. It assumes the hyperfine splitting constant for a proton connected directly to a carbon to be proportional to the net pi spin density on that carbon. And the McConnell relation looks like AH equals Q by rho, where AH is the hyperfine splitting constant. Thus, if the unpaired pi-electron density is twice on a carbon compared to another carbon, the hyperfine splitting constant should be correspondingly large for the former case. The Hückel molecular orbital method tells us that the net spin density at a particular carbon J due to an unpaired electron in the ith MO is absolute value of Cij square. This is actually only a first approximation to the spin density, but examination of the relation between the observed hyperfine splitting constants and the spin densities calculated in this way shows a very good correlation. The proportionality factor Q defined in the McConnell relation depends to a certain degree on the type of the pi electronic system we are investigating and the charge of the radicals.
So let us briefly summarize what we have learnt in this module. In this module, we have demonstrated how to calculate the charge densities on each atom contributing a pi electron on the basis of the Hückel molecular orbital method. We also showed how to calculate the bond orders in the Hückel molecular orbital approximation. We examined the relationship between pi bond orders and bond lengths and found an approximate correlation to hold between the two quantities. We also looked at if the Hückel molecular orbital theory can be applied to explain some of the electron spin resonance properties of unpaired pi electrons.